The program is about to begin. Kindly take your seats. Dear students, we are getting late. Kindly take your seats. Dear audience, make sure we all can enjoy and learn from this lecture. I did like to ask you to stay calm, stay seated, and keep your conversations to a minimum. Your attention is really appreciated. May I request everyone to kindly keep your mobile phones in silent mode to ensure the smooth conduct of the program. Good morning to all the respected dignitaries, invited guests, faculty members, students, and participants. A warm welcome to each one of you to the PK Iyengar Memorial Lecture organized as a prelude to the 38th Kerala Science Congress. The Kerala Science Congress, organized annually by the Kerala State Council for Science, Technology and Environment, continues to be a premier platform for scientific exchanges and interdisciplinary dialogue. This year, the 38th Kerala Science Congress will be held from 30th January to 2nd February 2026 at St. Albert's College Autonomous Ernakulam. As part of this year's academic programs, 9 memorial lectures have been instituted to honor the eminent luminaries in science, 7 of which have been conducted as preludes to the main events at the premier institutions in state. Today, we gather for P.K. Iyengar Memorial Lecture, paying tribute to Dr. P.K. Iyengar, a distinguished Indian nuclear physicist who played an important role in shaping India's nuclear science and technology programs, and one of the principal scientists behind Smiling Buddha. He also served as the director of Baba Atomic Research Center and later as the chairman of Atomic Energy Commission and the secretary of Department of Atomic Energy. Before we move to the formal ceremony, we will now watch a short video showcasing the initiatives of KSCSTE. Dear students, kindly keep your conversations to a minimum. Your attention is really appreciated.
Disconnected. Connected.
Erstwhile State Committee on Science, Technology and Environment, which was established in 1972. Kerala State Council for Science, Technology and Environment, popularly known as KSCSTE, was constituted in November 2002 to encourage and promote science technology related activities in Kerala State. It was done by reconstructing the erstwhile State Committee on Science, Technology and Environment, which was established in 1972 in concurrence with the science policy of the Government of India. Over the past 2 decades, KSCSTE spearhead the science and technology activities of the state in general and its own R&D centers in particular. With its headquarters in Thiruvananthapuram, 7 R&D centers, 3 grant-in-aid institutions, 2 centers of excellence, and 3 science parks are functional under the council. Our R&D centers are Center for Water Resource Development and Management, Kundamangalam, Kozhikode, Malabar Botanical Garden and Institute of Plant Sciences, Pukkunnu, Kozhikode, Kerala Forest Research Institute, PG Thrissur, Institute of Climate Change Studies, Kanjikuri, Kottayam, Srinivasa Ramanujan Institute of Basic Sciences, Vellur, Kottayam, Jawaharlal Nehru Tropical Botanic Garden and Research Institute, Palur, Thiruvananthapuram, National Transportation Planning and Research Center, Akulam, Thiruvananthapuram, Sophisticated Test and Instrumentation Center at CUSAT, Kochi, Community Agro-Biodiversity Center at MS Swaminathan Research Foundation, Wayanad, Integrated Rural Technology Center at Palakkad are the grant-aid institutions of KSCSTE. KSCSTE has also facilitated the establishment of Sri Chitra Tirunal Institute of Medical Science and Technology, Rajiv Gandhi Center for Biotechnology, National Center for Earth Science Studies, and Institute of Advanced Virology. At the headquarters, we initiate several programs to advance the science and technology objectives of the state. Programs for students include Scheme for Promoting Young Talents in Science, Student Project Scheme, and the Pradipha Scholarship for UG and integrated PG students. For researchers, we have KACST Research Fellowship for PhD scholars, Postdoctoral Fellowship for post PhD research, Partnering Academic and Industrial Research Scheme to promote translational research through academic industry linkage. Our programs for mid career researchers include Ecology and Environment Program, Science Research Scheme, and Engineering and Technology Program. Programs for women in science include Back to Lab Research and Postdoctoral Fellowship. These programs support women researchers with a break in career. KSCSTE also operates an entrepreneurship development program for SCST women in STEM. To support R&D initiatives from superannuated scientists, we operate the Emeritus Scientist Scheme. Selective augmentation of research and development and Shastra Bhoshani, science labs for government high schools in Kerala are 2 of our science infrastructure development programs. Under Shrestha program, KSCSTE nurtures Center of Excellence for World-Class Research in various domains. Our programs for technology development include APJ Abdul Kalam Youth Challenge Program, Rural Technology Program, Technology Development and Adaptation Program, and Engineering Support and Coordinated Research for Specially Talented Children. We initiate environmental conservation in the state by Environmental Information Awareness Capacity Building and Livelihood Program, National Green Corps, and Wetland Technical Unit. The Kerala Biotechnology Commission supports biotechnology development programs, which include biotechnology research support, schemes for industrial collaboration, and entrepreneurship development in biotechnology, Young Investigators Program in Biotechnology, Kerala Biotechnology Re-Entry Fellowship, Biotechnology Innovations for Rural Development, and our capacity building initiatives, notably the DBT Skill Vigyan Program and Human Resource Development in Biotechnology. Activities of the Patent Information Cell and the Intellectual Property Rights Information Centre Kerala facilitate IP awareness and patent related activities. KSCST Scheduled Caste and Scheduled Tribe Cell is a DST supported project that provides SNT solutions for the development of SC/ST communities. KSCST Shastra Puraskaram, Kerala State Young Scientist Award, and Science Literature Awards are notable science and technology awards instituted by the Council. KSCST is honored to recognize legendary scientists and science advocates through the Kerala Shastra Puraskaram. The National Children's Science Congress, Technology Festival, and Rural Innovators Meet are other important science popularization programs. KSCST also supports the observation of National Mathematics Day and National Science Day programs in the state. Kerala Science Park is a new initiative facilitated by KSCST for R&D development in the state. Centers of Excellence in Microbiome and Nutraceuticals are the two new initiatives facilitated by KSCST. Kerala Science Congress is an annual event of KSCST. The event includes 9 memorial lectures to honor the SNT visionaries and to cherish their contributions. Focal theme sessions, technical sessions bring together researchers in various domains. National Science Exhibition is another highlight of the Kerala Science Congress. Sessions like Walk with Scientists, SciSoul, PG Interaction Session are also organized as part of the event. The 36th edition of Kerala Science Congress evinces the presence of 2022 Nobel laureate in chemistry, Professor Morton P. Meldal, addressing the gathering. A celebration of science, innovation, and collaboration, the Kerala Science Congress has, through its many editions, united Nobel laureates, eminent scientists, and emerging researchers. It stands as a testament to Kerala's commitment to advancing knowledge, inspiring generations, and driving discovery for a better future. The 38th edition of Kerala Science Congress is scheduled from January 30 to February 2, 2026 at St. Albert's College, Ernakulam, with the focal theme Ocean Science for Blue Economy and Ecosystem Restoration. Kerala State Council for Science, Technology and Environment, advocating science and technology innovation in service of the state of Kerala.
It's now my privilege to invite our distinguished dignitaries to the dais. Dr. Arunan C., Senior Principal Scientist, KSCST. Professor Dr. Cynthia Catherine Michael, Principal, Fatima Mada National College. Dr. Sharon B.M., Scientist, KSCST. Dr. Anuraj V.L., Scientific Officer, Indira Gandhi Center for Atomic Research. Dr. Shaiju P.N., Assistant Professor of Botany, Fatima Mada National College. Dr. J.R. Jacob, Junior Scientist, KSCST. May I request the dignitaries to kindly occupy their seats on the dais. To formally commence the proceedings, I invite Dr. Arunan, Senior Principal Scientist, KSCST, to deliver the welcome address.
Respected Principal, Dr. Cynthia, our distinguished guest, Dr. Anuraj, my colleagues from KCST, Dr. Sherin, Dr. Jaya, Dr. Uh, Arshin Prasad, and dear students. എല്ലാവർക്കും നമസ്കാരം. ആദ്യമായിട്ട് പറയട്ടെ, ഞാൻ ഫാത്തിമ മാതാ നാഷണൽ കോളേജിൻ്റെ പൂർവ്വ വിദ്യാർത്ഥിയാണ്. 83-86 ഡിഗ്രി കെമിസ്ട്രി പഠിച്ചതാണ്. തീർച്ചയായിട്ടും നിങ്ങളുടെ മുമ്പിലേക്ക് വളരെ സന്തോഷമുണ്ട്. നേരത്തെ സൂചിപ്പിച്ച പോലെ 38ാം ശാസ്ത്ര കോൺഗ്രസിൻ്റെ മുന്നോടിയായിട്ടുള്ള ഒരു പ്രോഗ്രാമാണ് ഇപ്പോൾ നടക്കാൻ പോകുന്നത്. ശാസ്ത്ര കോൺഗ്രസ് എന്ന് പ്രധാനമായിട്ട് ഉദ്ദേശിക്കുന്നത് തന്നെ റിസർച്ച് സ്റ്റുഡൻസും അക്കാഡമിഷ്യൻസും ഗവേഷകരും ഒക്കെ ഒന്നിച്ചു ചേർന്നുള്ള ഒരു പ്ലാറ്റ്ഫോമാണ്. അവരുടെ റിസർച്ച് ഐഡിയാസ് ഷെയർ ചെയ്യാനും നോളജ് ഷെയർ ചെയ്യാനുമുള്ള ഒരു പ്ലാറ്റ്ഫോമാണ് നമ്മൾ പ്രധാനമായിട്ട് ഉദ്ദേശിക്കുന്നത്. കഴിഞ്ഞ 37 വർഷമായിട്ട് യാതൊരു തടസ്സവുമില്ലാതെ നടക്കുന്ന ഒരു പ്രോഗ്രാം കൂടിയാണിത്. പ്രത്യേകിച്ച് നിങ്ങൾ ഇന്ത്യൻ സയൻസ് കോൺഗ്രസുമായിട്ട് നോക്കുമ്പോൾ അത് ഇടയ്ക്ക് വെച്ച് നിന്നുപോയെങ്കിലും നമ്മൾ കോവിഡ് ടൈമിൽ പോലും യാതൊരു മുടക്കവും കൂടാതെ നടത്തി വരുന്ന ഒരു പ്രോഗ്രാമാണിത്. കേരള സയൻസ് കോൺഗ്രസിന് വിവിധ ഘടകങ്ങളാണുള്ളത്. ഇപ്പോൾ പറഞ്ഞ പോലെ മെമ്മോറിയൽ ലെക്ചേഴ്സ് ഉണ്ട്. അതിന് പുറമെ നമുക്ക് PG ഇൻട്രാക്ഷൻസ് ഉണ്ട്, വോക്ക് വിത്ത് സയൻറ്റിസ്റ്റ്, സ്കൂൾ കുട്ടികൾക്കുള്ള വോക്ക് വിത്ത് സയൻറ്റിസ്റ്റ് ഉണ്ട്, പിന്നെ ടെക്നിക്കൽ പേപ്പർ പ്രസൻറ്റേഷൻ ഉണ്ട്, പിന്നെ സൈസോൾ എന്ന് പറഞ്ഞാൽ വേറെ സ്പെഷ്യൽ പ്രോഗ്രാംസ് ഉണ്ട്. ഇങ്ങനെ വൈവിധ്യമാർന്ന പ്രോഗ്രാംസ് ചേർന്നതാണ് സയൻസ് കോൺഗ്രസ്. 38ാം ശാസ്ത്ര കോൺഗ്രസ് നേരത്തെ സൂചിപ്പിച്ചതുപോലെ സെയിൻറ്റ് ആൽബർട്ട്സ് കോളേജ് എറണാകുളത്ത് വെച്ച് ജാനുവരി 30 മുതൽ ഫെബ്രുവരി 2 വരെ വിവിധ പ്രോഗ്രാമുകൾ നടക്കുകയാണ്. എല്ലാവർക്കും അതിലേക്ക് സ്വാഗതം. സയൻസ് കോൺഗ്രസിൻ്റെ പ്രധാന ഘടകങ്ങളൊന്നായ മെമ്മോറിയൽ ലെക്ചേഴ്സ് നേരത്തെ സൂചിപ്പിച്ച പോലെ 9 പ്രോഗ്രാംസ്, 9 മെമ്മോറിയൽ ലെക്ചേഴ്സാണുള്ളത്. ഇത് ആദ്യകാലങ്ങളിൽ സയൻസ് കോൺഗ്രസ് വേദിയിലായിരുന്നെങ്കിലും ഇതിൻ്റെ ബാഹുല്യ നിമിത്തം നമുക്ക് ആ വേദിയിൽ നടത്താൻ സാധ്യമല്ല. അതിനാൽ 7 മെമ്മോറിയൽ ലെക്ചേഴ്സ് എപ്പോഴും നമ്മൾ സയൻസ് കോൺഗ്രസിൻ്റെ പ്രില്യൂഡായിട്ട് മുന്നോടിയായിട്ട് നടത്തുകയാണ് ചെയ്യുന്നത്. അതിലൊന്നാണ് ഇപ്പോഴും നടക്കുന്നത്. നമുക്ക് വളരെ ഭാഗ്യമുണ്ട്. ഡോക്ടർ അനുരാജ് വളരെ പ്രശസ്തനായ ന്യൂക്ലിയർ സയൻറ്റിസ്റ്റാണ്. അയ്യങ്കാറിൻ്റെ ഓർമ്മയുടെ ഭാഗമായിട്ട് അദ്ദേഹം മെമ്മോറിയൽ ഒറേഷൻ നടത്താനായിട്ട് അദ്ദേഹത്തെ വിളിച്ചത് നമ്മൾ തീർച്ചയായിട്ടും ഭാഗ്യമുള്ളവരാണ്. ഞാനെൻ്റെ കർത്തവ്യത്തിൽ കിടക്കുകയാണ്. ആദ്യമായിട്ട് നമ്മുടെ അധ്യക്ഷയായിട്ടിരിക്കുന്ന ഡോക്ടർ സിന്ധ്യ, നിങ്ങൾക്ക് എല്ലാവർക്കും പരിചയമുള്ള പ്രിൻസിപ്പളാണ്. തീർച്ചയായിട്ടും നിങ്ങളുടെ എല്ലാം വളർച്ചയുടെ ഭാഗമായിട്ടുള്ള ടീച്ചറിനെ ഞാൻ ഇതിലേക്ക് സ്വാഗതം ചെയ്യുന്നു. നമ്മുടെ വിശിഷ്ടാതിഥി ഡിസ്റ്റിംഗ്വിഷ്ഡ് സ്പീക്കർ ഡോക്ടർ അനുരാജ്, Iyengar സീനിയർ സയൻറ്റിഫിക് ഓഫീസറാണ്. അദ്ദേഹത്തെയും ഈ വേദിയിലേക്ക് സ്വാഗതം ചെയ്യുന്നു. പിന്നെ എൻ്റെ പ്രിയപ്പെട്ട കൊളീഗ്സായ ഡോക്ടർ ഷെറിൻ, ഡോക്ടർ ജയ ജേക്കബ്, പിന്നെ മറ്റ് സുഹൃത്തുക്കൾ, ഇവിടുത്തെ മറ്റ് സുഹൃത്തുക്കൾ, സ്റ്റുഡൻസ് എല്ലാവരെയും ഈ വേദിയിലേക്ക് സ്വാഗതം ചെയ്യുന്നു. താങ്ക് യു.
Thank you, sir. May I now invite Professor Dr. Cynthia Catherine Michael to deliver the presidential address.
A very good morning to one and all. Respected dignitaries on the dais, esteemed scientists from the Kerala Science Congress, distinguished guests, respected faculty members, and my dear students. It is with immense pride and joy that I preside over this seminar organized in collaboration with the Kerala Science Congress at Fatima Mada National College, Kollam. Today it is just not an academic gathering. It is a celebration of curiosity, inquiry, and the courage to think differently. As Kerala stands apart in the history of India for its commitment to education, rational thought, and social justice, our state has shown the nation that progress is possible when knowledge is placed at the center of development. Yet, in a rapidly changing world marked by climate crisis, technological revolutions, and social transformations, Kerala must now take the next step from learning knowledge to creating knowledge through research. As we look around, our rivers, backwaters, coastline, they all tell stories of environmental change. Our communities face challenges related to health, livelihoods, sustainability, and digital transformation. These are not distant problems. They are local realities waiting for thoughtful solutions. Research gives you, dear students, the power to turn concern into understanding and understanding into action. So we have to ask questions, ask ourselves and ask others. Why is this happening? How can this be improved? Once you ask these questions, you have already stepped into the world of research in order to find solutions for our current problems. At Fatima Mother National College, we believe that every student has the potential to be a researcher. Our role as educators is to kindle that spark, to guide you, to encourage you, and to create opportunities for exploration. I place on record my deep appreciation for our faculty members of the science departments, especially Department of Botany, who mentor for conducting this program, and all the faculty members, not only science but also the arts, because research is prevalent. It should be there in the mind of all students, who mentor our students and nurture the spirit of inquiry with dedication. And as we all know, the Kerala Science Congress has always been a beacon in promoting scientific temper and student participation from the state. I thank the Kerala Science Congress for taking Fatima Mother National College as a venue for this program, and welcome all the scientists who have accepted our invite and are present here today to our college. I congratulate the departments for taking the initiative to conduct this program. And dear students, there should be something that you should take away from this program and start thinking for solutions where you can be the change makers in the society. Wish you all the best. I hope you have a nice day. Thank you.
Thank you, ma'am. It's my privilege to hear from Dr. Sharon BM, scientist KSCST. Ma'am, requesting you to present a brief introduction to the life and contributions of Dr. P.K. Iyengar.
Good morning. Distinguished speaker and chief guest of the day, Dr. Anuraj, Scientific Officer G, Indira Gandhi Center for Atomic Research, President of the function, Dr. Cynthia Catherine Michael, Principal, Fatima Mother National College, Dr. Arunan, Senior Principal Scientist, KCST, Dr. Shaiju PN, Dr. Jaya Jacob, Sri Arjun, esteemed faculty, and most importantly, the young scientific minds of tomorrow who are sitting in front of me. It is a profound honor to stand before you today to introduce a man whose life was not just a career in science but a masterclass in nation building, Dr. P.K. Iyengar. Dr. Padmanabhan Krishnagopala Iyengar was born on 29 June 1931 in Tirunelveli, Tamil Nadu. He earned his graduation in physics from the University College Thiruvananthapuram and his post-graduation also from the University of Kerala. He joined the Tata Institute of Fundamental Research in 1952 and soon became an ardent pupil of Dr. Homi Baba, Dr. Vikram Sarabhai, and Dr. Raja Ramanna, and all such other stalwarts. Dr. Iyengar was sent to the Chalk River laboratories of the Canadian Atomic Energy Establishment to work under Dr. B.N. Brockhaus, a Nobel laureate in physics. Those were the early days of the dawn of nuclear power, and the sharp intellect of Dr. Iyengar took no time in grasping the intricacies of the new technology that was taking shape. Upon his return to India, Dr. Iyengar joined the Atomic Energy Establishment Bombay, later renamed as the Baba Atomic Research Center (BARC), where he built up a team of capable world-class research in neutron scattering and experimental nuclear physics. In 1960s, Dr. Iyengar took a leading role in the design and commissioning of the Purnima-1 plutonium reactor. Purnima validated India's capability in fast reactor design, influencing later projects such as the Smiling Buddha. On 18th May 1972, under Dr. Iyengar's leadership, Purnima achieved its first criticality, its initial self-sustaining nuclear chain reaction, making a major step in India's fast reactor technology. This success paved the way for the 1974 Pokhran-1 Operation Smiling Buddha, India's first peaceful nuclear explosion exactly 2 years later, where Dr. Iyengar served as a key scientist under Dr. Raja Ramanna. A few hours before the nuclear test, Dr. Homi Sethna, then chairman of the Atomic Energy Commission, was reported to have asked at Pokhran, whose head will roll if the device does not explode? To this, Iyengar replied, if the laws of physics work, it will work. In 1984, Dr. Iyengar became the director of the Baba Atomic Research Center, where he successfully completed the commissioning of the Dhruva reactor. At BARC, he didn't just manage scientists, he mentored them, and in 1990, he was appointed the chairman of the Atomic Energy Commission of India and secretary to the Department of Atomic Energy, guiding India's nuclear power program through expansion, including commissioning new reactors and boosting indigenous capabilities. After his illustrious career at the national level, Dr. P.K. Iyengar brought his immense scientific expertise to Kerala, where he played a pivotal role in shaping the state's science and technology policy framework. During the years 1992 to 93, he served as the state committee member of the Science, Technology and Environment Committee, the precursor of the present-day KCST, expanded as the Kerala State Council for Science, Technology and Environment. His association with STEC came at a formative stage, and his contributions helped strengthen the institutional foundations that continued to guide KCST and the science and technology initiatives in the state taken up by KCST. From 1994 to 97, Dr. Iyengar provided visionary leadership as the chairman of the Science, Technology and Environment Committee and ex officio secretary to the Government of Kerala, steering the committee towards clearly defined regional research priorities and mission-oriented programs. Simultaneously, during the period 1994 to 1998, he served as a scientific advisor to the Government of Kerala, ensuring that science and technology considerations were integrated into the state's development planning agendas. Further extending his influence from 1996 to 1998, Dr. Iyengar was a member of the State Planning Board of Kerala. In this capacity, he was instrumental in integrating science and technology into the state's 5-year plans, ensuring that scientific advancement wasn't just a buzzword but a budgetary reality. His leadership underscored the importance of aligning science policy with sustainable development and education, themes that still resonate in the state's science ecosystem. Dr. Iyengar's distinguished career was marked by numerous prestigious honors, including the Shanti Swarup Bhatnagar Prize in 1971, one of India's highest recognitions for scientific research, followed by the Padma Bhushan in 1975 for his outstanding contributions to the nation. In addition, he received several eminent awards such as the Federation of Indian Chambers of Commerce and Industry Award, the Raman Centenary Medal, the Baba Medal, and the R.D. Birla Award, among many others. Dr. P.K. Iyengar's life was a remarkable blend of scientific excellence, visionary leadership, and service to society. From pioneering India's nuclear research infrastructure to guiding science policy in Kerala, His contributions were both deep and wide. Let us honor his memory not just by remembering his achievements, but by continuing the pursuit of knowledge with integrity, creativity, and purpose. Thank you.
Thank you, ma'am. May I request Dr. Shaiju PN, Assistant Professor of Botany, Fatima Mother National College, to introduce the speaker of the day. Sir, please.
Good morning. Respected dignitaries of the dais, on the dais, dear fellow staff members, research scholars, and students. It is my privilege to introduce today's speaker, Dr. Anuraj VL, who is a scientific officer G and head of the core safety analysis section in the reactor neutronics division, reactor design group at the prestigious Indira Gandhi Center for Atomic Research, Tamil Nadu. Dr. Anuraj has extensive expertise in reactor neutronics, core design, and safety analysis, playing a pivotal role in ensuring the safety and performance of advanced nuclear reactor systems. His work significantly contributes to the design and analysis of reactor cores with a strong emphasis on safety margins and regulatory compliance. With his deep technical knowledge and leadership in reactor safety analysis, Dr. Anuraj continues to make valuable contributions to India's nuclear energy program. Dr. Anuraj specializes in the design, optimization, and safety of fast breeder reactors with a primary focus on mitigating nuclear accidents and ensuring core stability. As the head of the core safety analysis section, Dr. Anuraj is responsible for demonstrating the neutronic safety of advanced Indian fast reactors, including the fast breeder test reactor and prototype fast breeder reactor. His technical contributions include developing and utilizing various computational tools for comprehensive FBR safety and stability analysis. His doctoral research specifically focused on the stability characteristics of both mixed oxide and metal-fueled fast reactor cores, providing a deep theoretical foundation for the practical work. We are honored to have him with us today, and we look forward to his insightful talk. On behalf of the Fatima Mother National College, I sincerely thank Kerala State Council for Science, Technology and Environment for choosing as the venue to organize this prestigious endowment lecture in connection with 38th Kerala Science Congress. Thank you all.
Thank you, sir. We now come to the highlight of today's program, the Dr. P.K. Iyengar Memorial Lecture. It's my honor to invite Dr. Anuraj VL, Scientific Officer, Indira Gandhi Center of Atomic Research, to deliver the memorial lecture. As we proceed, the dignitaries on the dais may kindly occupy their seats off the dais.
Good morning to all, dear students, respected Principal Dr. Cynthia Catherine Michael, and Dr. Arunan sir, Dr. Sharon BM, Dr. Jay Jacob from KSCSTE, and Dr. Shaiju PM from College. Welcome to all. So before delivering the lecture, I would like to thank the organizers for inviting me to deliver this P.K. Iyengar Memorial Lecture at the Fatima Mata College. P.K. Iyengar is an eminent personality of our department who had made significant contributions in both strategic and civil nuclear applications. He played a pivotal role in our first peaceful nuclear test at Pokhran, and also for our center, Indira Gandhi Center, which basically working on plutonium-based systems. He is the first person who has generated the background data using the Purnima critical facility. So we are actually oblique to his contributions, uh, uh, and the current program relying on his the data generated by him at the earlier stages. So thank you for inviting me here, and all the people who are working behind the curtain, both from the Kerala Science CSTE and Fatima Mada, my sincere thanks. So let me start my presentation.
May I request everyone to kindly keep your mobile phones in silent mode to ensure the smooth conduct of the memorial lecture. Dear students, please keep your conversations to a minimum. Your attention is really appreciated.
Power. Hello. Am I audible to all the people? Slide change. So good morning to all. So I am working in the field of nuclear energy. So today, rather than presenting the achievements we have made in the department, better I would prefer to pose a problem that you may have to solve in the future. That is to ensure the energy security of our country. So what is the problem, and where are the things we are lagging, and how you can contribute to that? That will be the soul of the presentation. So I have titled it as Igniting the Atom, the Science of Sustained Fission. So you might have heard of nuclear fission, which is a very green, enormous source of energy which is available to mankind. And sustaining that fission reaction inside a reactor, that is one challenge. Another thing is sustaining such reactors using the available resources to produce the energy that we require for the rapid industrial growth. So both the way, the sustainability is an important theme in the context of nuclear energy. So, so why we have to listen to this kind of lectures? Why I should talk? That is the context of the lecture. So here I have given two global maps, world maps. Both are contour maps. So first one, red one is the per capita energy consumption for each country. The darker the color, the more energy is available to the citizen. The second blue one is actually the Human Development Index. So what is the life standard of people in each country? So there is a one-to-one correspondence. If you are provided with more energy, there's a better chance you have a better lifestyle. So if we plan to have a developed nation, so our government is planning to achieve it as close as to 2047, 100 years after independence. So such a goal brings to the requirement of energy. So now there is a high uneven platform around the globe on this energy availability. For example, United States per capita energy consumption is 70,000, where in India it is only 7,000. Even world average is 3 times, 21,000 units are available per person. So we need to make it 10 times, we have to triple it 5 times, 10 times, then only the, the goal of a lifestyle which is comparable to all the developed nations can be achieved. So, but in the recent past, there is another problem. That is, we cannot use any energy source like the conventional energy sources like the coal or oil. Because if you burn coal, you are actually producing carbon dioxide. This carbon dioxide is a harmful thing. In the present age, we are much worried about the global warming and the consequences on the weather patterns. So we cannot use this traditional coal and fossil fuel power plants to produce electricity. We have to go green. We have to more depend on renewable energy sources like solar, wind, and other options. So in 2021 itself, we have committed in the international platform that by 2070, we will make the carbon emissions zero. We should close all our coal plants and we should close all our oil-based plants to achieve this actually. Then what are the other options? So if you see per unit electricity production, how much carbon dioxide equivalent particles are emitted, you can see in coal per every gigawatt hour of electricity, 970 ton of carbon dioxide is emitted. And similar the case of oil, natural gas, etc. And only solar, wind, and nuclear are producing less carbon dioxide. So solar also produces carbon dioxide because of its manufacturing process and other associated production pathways. In this aspect, nuclear is the one which emits minimum amount of carbon dioxide and minimum amount of pollution. So, with this objective from around 2014-15 itself, you can see this is the capacity in the y-axis, that installed electricity generation capacity in the country, and the x-axis is the year. So we can see the black one, which is the coal production capacity, which becomes stabilized. There is not much growth in the coal plants. But the yellow region, that is the solar plants. So we have made a significant improvement in the installation of solar panels, and major share of our installed capacity now reached from the solar. In the last November, actually we crossed the 50% threshold. So 50%, more than 50%, 51 I guess, of electricity now is installed capacity is now from renewable energy sources. 48% is coming from this carbon emitting coal and oil. Okay. So this is 2025. Solar is constituting up to 25% of installed capacity, and wind is 11%, and coal is only 44%. But with these renewable energy sources, we have another problem. Because solar availability is limited, right? It depends on the time of the day, it depends on the month of the year. Wind also seasonal. You cannot utilize that installed capacity at 100% rating throughout the year. But once you start a coal plant, it will produce the same amount of energy through the entire time of operation, and it can be operated uninterruptedly if coal is available. So, even though the installed capacity is more than 50%, actual share of electricity, if you see, still our country is mostly depending on coal-powered plants. Actually, 70% of electricity is still coming from coal, and we are promised we are going to shut down these plants soon. What are the other options? Whether we have oil resources, or even if oil resources we have, you cannot use them. We have only coal. We don't have a uranium, but we have plenty of sunlight. Yes, of course, because of our position on the globe, we can use solar, but solar cannot use with the availability factor. 100% availability factor is not there with the solar. So then the only option we have is look at nuclear. If you want to reduce carbon dioxide, and if you want a baseload power supply, uninterrupted power supply, the only option we have is nuclear. Okay. Then of course you all will be now wondering, sir, no nuclear, right? Why no nuclear? Are you afraid of nuclear energy? Your personal opinion. Yes, right? Because you watched the movie Chernobyl, the documentary. So there are so many media informations you will be gathering that this nuclear will affect your generations, radiation hazards, nuclear waste, the evil energy, right? But still governments are making reactors, right? Every government is making new reactor. Why? Because when you look at the data, this is per terawatt hour, how many human casualties happened in the history. So coal will cause 24 casualties per terawatt hour because coal you have to mine, you have to ship it, and it pollute the environment, right? The processes associated with the coal and oil, they are much more harmful than solar, nuclear, and wind. So nuclear, if you see the casualties, actual casualties by radiation, if you see per terawatt, we should look at the statistical number, not with the prejudices. So nuclear is very close to solar and wind itself. Okay, you heard of the Fukushima accident, most catastrophic nuclear accident. Nobody died. Chernobyl was the only one accident. 30 people died. But we read coal accidents every day in newspaper, mine and all. We don't worry. Okay. So governments will always support across the globe nuclear because it is green and it is less harmful for human. Only thing is there are some technical aspects which still has to be addressed, that we will discuss in this presentation. That are the challenges we have to solve. Another reason for us is we may not have oil, we import them. We don't have even uranium. We have very limited, modest supply of uranium. Recently, some resources we could find. But we have thorium. And as a Keralite, we should be more proud because most of this thorium is here, our district, right? The coast of Kerala, we have monazite sand. And it is having this thorium isotope, thorium-232. This is huge, vast amount of thorium, such a way that even the 1/4 of the entire global deposit of thorium is across our coast. Only problem is thorium we cannot directly load into the reactor because it is not a fissile material. It is not a nuclear fuel. But we can always convert this thorium to a nuclear fuel. We have to just develop that technology. Okay? Then if we can use this thorium for nuclear energy production, the promise is even for the next generations to come, you don't have to worry about energy problem. Right? That much amount of thorium is already available in our country. We don't have to depend any tariff, any foreign problems. Energy will be guaranteed if we use thorium. And that is not a simple task. And this is your problem. Okay? Study well, solve this. So how we can use thorium? For that we should know what is nuclear energy. The students from the physics background may already know, plus 2 level also you might have studied. Nuclear energy can be produced in 2 ways. One is nuclear fusion and the other is nuclear fission. Nuclear fusion means you have 2 lighter elements, you fuse together and make a bigger atom. Lighter means like hydrogen or deuterium or tritium. If you can fuse them, they will become a more stable atom, and in that process it will emit energy, and this is the reaction which happens in sun. Actually, all energy on earth is a derived energy from fusion. Solar, wind, coal, petroleum, all these are actually originally formed when this matter is converted to energy in the sun. Okay. Second is nuclear fission. So nuclear fission have one drawback, that is to bring 2 light elements close together is very difficult because they are positively charged nucleuses. They repel due to Coulomb repulsion.
So you need to supply high kinetic energy to bring two positively charged atoms together. That need plasma conditions, very high temperatures, and containing the temperature is difficult. So this work is only in the research stage, but this is supposed to be the future energy source for humans. Now, nuclear fission, if you see, it is much simpler. Even it can happen spontaneously as a mode of radioactive decay. Many atoms on Earth, like uranium 238 and some other isotopes, which are found on Earth itself, already doing this fission. Means a super heavy atom like uranium, which have 235 nucleons inside the atom nucleus, it will split its own for stability. In that process, it will emit radiation. So this spontaneous fission is a process which help in, like you see, deep space explorations. You can use this material as a battery. It will produce energy based on its half-life, right? Chandrayaan mission, when the sun is on the other side, we couldn't operate the machine, right? But if you have a nuclear battery in that, then it can give the uninterrupted power supply for many years, actually, for 100 years straight away. Voyager 1, Voyager 2, all are powered by this nuclear batteries, depending on spontaneous fission or spontaneous emission of alpha particle. Another is induced fission. That means you project a neutron or particle to the nucleus, and after absorbing that particle, the nuclei will split into two. This kind of fission is called induced fission, and this is the reaction which we are using to make commercial nuclear reactors. And the particle which split the nucleus is a neutron. Okay, we fire a neutron at an atom, and the nucleus will absorb that neutron and become unstable, and it will split. And during that splitting, it will emit energy. And that energy we convert to electricity. Now, for reactor language, this induced fission itself, we have divided it into two subcategories. One is if the incoming neutron is of very low energy, which is at thermal equilibrium with the surrounding medium, like 0.025 eV, very low energy, then the fission induced by such low energy neutrons are called thermal fission. And the neutrons induced by high energy neutrons are called fast fission. So we have two types of reactors working on both thermal neutrons that are called thermal reactors, and if you use a high energy neutron to split the nucleus, we call them the fast reactors. The fast reactor doesn't mean the reactor is very fast. Okay. Fast reactor means the neutron which is used to split the atom is fast moving. Now this figure you might have seen so many places. This is the fission event. There's a heavy nuclide like uranium 235, and a neutron is absorbed, hitting on that nucleus, and it gets absorbed, and then it will become uranium 236. Mass number will increase by 1 because one more neutron we have added. This nucleus have 92 protons and 143 neutrons. Very heavy nucleus. For 92 protons, there is 143 neutrons. Why? Any science student can answer that? Carbon, how many protons and how many neutrons? Carbon. Chemistry. How many protons? What is atomic number of carbon? Carbon is 6. You know this, right? Carbon atomic number is 6. Number of neutrons is again 6. Oxygen atomic number is 8. Number of protons and number of neutrons are same. But once you go heavier, you need a large number of extra neutrons for stability, because the strong force which holds the nucleons together is very short range. But the Coulomb repulsion between the protons is strong and it is longer range. Right? It's a Coulomb force. It has infinite range actually. So to overcome the Coulomb repulsion, you need more and more neutrons as you go heavier and heavier in the periodic table. So uranium 235 have a large number of extra neutrons, not extra neutrons, it is required for stability. Now when it splits, the nucleus doesn't need that many neutrons. Suppose in this example, it can split in many ways, but in the figure I have given iodine 135 and yttrium 97. These two daughter nucleides are formed. This daughter nuclei doesn't require that many neutrons. So what does it do? It just emits that neutrons, release the neutrons. So 2 to 3 neutrons will be emitted along with this fission event. And these neutrons are of very high energy, 2 MeV. And along with that, an energy of approximately 200 MeV will be released as the kinetic energy of that fission products. That means this yttrium and this iodine will be moving with very high velocity, and it will heat the medium, and that heat we remove using the coolant. Okay? That is how we produce energy using nuclear fission. Now, these neutrons which are produced along with the fission are called Prompt neutrons. And the fission products which are produced, I told you, they are also neutron rich. Since they are lighter elements, that doesn't require that many neutrons. So it has to reduce the neutron number, or it has to increase the proton number. And there is one radioactive decay which supports that, that is beta decay. In a beta decay, a neutron will become proton and electron, conserving the charge and mass. So in a beta decay, a neutron will change to proton. So the atomic number will increase by 1 and the mass number will remain same. So iodine will become xenon 137 and that xenon 137. And these fission products, whatever I told, 2 atoms are given. But actually in a reactor, 1500 type of different nucleides are formed as fission products. So 2 examples given here. Out of this 1500, at least 50 are after radioactive decay may release a neutron. So this iodine will decay to xenon, and this xenon have a potential to release an extra neutron, and that neutron is called delayed neutron. Why I am mentioning this, I will tell you. Without delayed neutron, nuclear reactors are not possible. I will tell you in the next slide. Now, why uranium-235? So uranium-235 is an isotope of uranium. Now, this graph actually represents the probability for the atom to undergo fission. X-axis is energy of the neutron, which is causing the fission. Y-axis is the probability. Probability is measured as cross-section. Okay, it's a scientific term you may be knowing. So you can see if the energy is less, the cross-section or the probability for fission is high. When the energy is high, the y-axis is logarithmic scale, okay? So if the neutron energy is high, like MeV, then the probability to cause fission is relatively less. Actually 1 by 1000 times of the thermal neutron. So thermal fission is much more probable than a fast fission. So if the energy of the neutron is less, it can be thought of like this. If the neutron is moving very slowly near the uranium atom, it have higher probability for interaction. Okay. If it go very fast, it will not interact. It's just a common language, but difference it can be explained in using quantum mechanics. Now these elements, uranium-235, uranium-233, and plutonium-239, these 3 isotopes have very high probability for neutron-induced fission. And these isotopes are called nuclear fuel. Okay? Nuclear fuel. And these materials are called fissile materials. Fissile material means I give any energy of neutron, it will split. But unfortunately in nature, plutonium-239 is not there. Our Earth doesn't have plutonium-239. Uranium-233, not available. The only isotope which can undergo fission is uranium-235. That also very little amount. If I mine uranium from the earth crust, 99.3% is uranium-238, which have a higher half-life, 10 to the power 7, and uranium-235 is only 0.7%. So the fuel which I can use in a nuclear reactor is only available 0.7% in the uranium which we are mining. So this uranium-238 and thorium-232, these 2 elements are plenty available, but they are not fissile. But there are reactions by which we can convert these isotopes into fissile materials. So the isotopes which can be converted to fissile material are called fertile. So uranium-238 and thorium-232 are 2 fertile isotopes which are abundant. But the problem is we have to irradiate these isotopes with neutrons So if uranium-238 absorb a neutron, it will become 239. Then it will undergo a beta decay to become neptunium-239, and one more beta decay, it will become plutonium-239. So plutonium is a man-made element. So you have studied in the periodic table, there were many elements missing, right? Most of the missing elements are filled by nuclear reactors actually, by irradiating the other isotopes, okay? Now, similar to that, thorium-232, which is in our case, we have plenty. If you irradiate it to neutrons, it will become thorium-233, then it will become promethium-233, and later it will become uranium-233, which is a nuclear fuel. So we can convert uranium-238 and thorium-232 to nuclear fuel by using the same nuclear reactors. This kind of conversion is called conversion or breeding is called the production of fissile material. Okay. Now, how to sustain a fission reaction inside the reactor for getting that uninterrupted power supply? You heard of chain reaction? I think 9th standard it is there. There, right? Chain reaction. Okay. So one neutron is absorbed by a fissile metal uranium-235. It is split into two. Now two daughter nucleides are there, which are moving at very high kinetic energy. And along with that, 2 to 3 neutrons also will be released. And these neutrons can bombard on the other uranium-235 atoms and split them, right? Then again more neutrons will be produced, and these neutrons will cause fission in other uranium-235 atoms available, right? Like this, you can increase this geometric progression, right? Every generation, it is 3 times the previous, right? Like that, you can increase. And this is why nuclear weapons are catastrophic. So the time scale involved from the first fission to the next generation is 10 to the power minus 7 seconds. So in 1 second, how many generations will happen? 10 to the power 7. And in each generation, you are multiplying by 3. Assume the potential. So a huge, tremendous amount of energy can be released in a fraction of a second. And that is why this kind of uncontrolled chain reaction is so catastrophic, and every country wants to have this weapon. Now, for power production that we are interested in, we don't want this uncontrolled chain reaction, right? We have to limit it. If one fission is happening in this generation, I need only one fission next. I don't want the increase in the fission rate. I want steady fission rate. 1000 fission in this generation, next generation also 1000 fission, so that I will have a consistent, steady output power. For that, we have to control this reaction, and that control is achieved by, first thing is, whether enough uranium-235 atoms are available for the neutron. If I load natural uranium, as I told you, 99% will be uranium-238. So the neutrons will get absorbed by 238 only, right? So sustaining chain reaction will be difficult. So one option is, I keep some moderator so that the MEV neutron will be thermalized. Thermalized means when the neutron hit on the hydrogen atom, and when it gets scattered, its velocity decrease, right? You have two-body problem, that particle collision problem. I just studied already, I guess. So the energy transfer, when one ball hit on another ball of same mass, M1, M2, classical mechanism, last study. So there will be a kinetic energy transfer, and the projectile particle which hitting and coming back, it will have a lower velocity. Some amount of kinetic energy will be transferred to the other particle. So we can use carbon, hydrogen, deuterium, such lighter elements which have similar mass as of a neutron, so that an amount of energy can be transferred to that atom. Such materials are called moderator. Now, if I keep a moderator medium, most common one is water. So if you use water there, the scattered neutrons will have a lower energy. So when I reduce the energy of the neutron, we have higher potential for fission reaction to happen. I told you in the graph, right? Probability of fission is higher if the energy of the neutron is less. So if I use natural uranium, I have to use a moderator, and then the probability of fission is high. So instead of getting absorbed in 238, it will get absorbed in 235 and do the fission. Another thing is we should have some mechanism to arrest the chain reaction if it get diverges. For that we use some neutron absorber like cadmium, boron. So these kind of elements we insert into the reactor as control rods. Okay. So when it goes in, it will absorb the neutrons and reduce the neutron population in the core. Now, here suppose I design a reactor such a way that 3 neutrons are produced, 1 neutron is absorbed by other materials, or 1 neutron is leaked, escaped the core, 1 neutron is causing fission in 235, 1 neutron is converting uranium 238, a fertile material, to plutonium 239. Then, each time I consume one fissile atom, uranium 235, I will be producing another fissile atom, plutonium 239, right? This 238 is a fertile material, 238. It will absorb neutron and become plutonium 239. So in a nuclear reactor, I can sustain the chain reaction along with production of fuel itself. Okay. Any other plant, when you burn fuel, it will just get exhausted, right? At the end of the cycle, there is no more fuel. That's all. Coal will become ash. Your bike petrol tank, it will become empty. Okay. But here, if I have more than 2 neutrons produced in fission, as I consume the fuel, I can produce fuel also. Such a reactor is called breeder reactor. Okay. Now, using this technology, whether we can convert the uranium 238 and thorium 232 to fissile materials and ensure energy security for the future. This is the challenge. Now, sorry, water break. What happens to the neutron inside the reactor? So I start with 1000 neutrons, this black color 1000 thermal neutrons. So, you know, in a reactor, actually what we do is we keep some fuel rods, okay, also vertical cylindrical rods of fuel, and in between the fuel we fill moderator, water, okay. And through the surface of this fuel we pass some coolant to remove the heat to the turbine. Okay, this is how the physical setup looks like. Now in this setup, if I give 1000 neutrons, if I give 1000 thermal neutrons to the fuel, around 1330 neutrons will be produced. I told there are more than 2 neutrons will be produced in fission, but all the 1000 will not lead to fission. Some will be absorbed by uranium 238. So if natural uranium, if I am keeping, only 1.33 is that factor, and that factor is called eta. Eta is the number of neutrons produced per number of neutrons absorbed. So in a mixture of uranium 235 and 238, that factor is only 1.33 if you use natural uranium. Now this 1330, all the neutrons are of high energy. So this high energy neutron have potential to split some amount of fertile nucleides also. You know, natural uranium have 99% 238. Some of them will undergo fission when the incident neutron is having very high energy. That is a threshold fission. Okay. Now this 1330 will become 1370, but these neutrons, some of them may escape through the surface of the reactor. So reactor has some finite size, and neutrons are having very high kinetic energy, so just they escape the reactor. That is called the leakage. So suppose 70 neutrons are leaking, the remaining 1300 are there, that will be entering the moderator. Now moderator job is to reduce the energy of the neutron. While reducing the energy, actually there are resonance cross sections in the uranium 238 absorption bundle. There are so many elements which will absorb with resonance reactions, you know. I assume again. So resonance reactions are there which have very high probability to happen at some particular energies. So how many neutrons will survive this resonance region when its energy is reduced from MeV to EV? That is called resonance escape probability. So now we have 1170 neutrons survived. Out of them, these all are thermalized now. 50 neutrons will leak again. Thermal neutrons also will escape the reactor. So the balance out of 1120, you have to use some coolant, you have to use this moderator, you have to use some steel cladding to place your fuel. All these mediums will absorb some neutrons. Okay, they also have potential to absorb neutron. For example, hydrogen will absorb neutron and will become deuterium. Okay, so such absorption will take away some neutrons. So with this, all the processes, finally I should end up with the same 1000. So in one generation, if I have 1000 neutrons, then it will cause fission, it will move with high energy, then it will get moderated, it will get absorbed in other medium, parasitic mediums. Then finally, if same 1000 is available, then I can sustain the chain reaction. I can sustain the power production at constant 500 or 1000 megawatt capacity. So to achieve this, we have to design the reactor such a way that if I use natural uranium, the eta is very small. Then I cannot use light water, H2O, for coolant or moderator, because hydrogen will absorb the neutrons. So we have to use heavy water. Heavy water means in H2O, we replace hydrogen with deuterium. Deuterium is an isotope of hydrogen, which have one neutron. Okay, hydrogen, deuterium, and tritium. These three isotopes are there for hydrogen. So it looks like water. By chemistry, it is water, but if you weigh it, it will be heavy, because every hydrogen atom have one additional neutron. Okay, so if I use deuterium water, then I can use natural uranium. So if you want to use light water to compensate for the hydrogen absorption, you have to enrich the fuel. So most of the Western countries, they enrich uranium. So they increase the percentage of uranium-235. Okay. And now how to reduce the leakage? A spherical reactor will have minimum leakage. Okay. Because for leaking, you need a surface area. The surface to volume ratio will be minimum if you have a sphere. Right? But a sphere, I cannot remove the heat efficiently. So usually we make cylindrical rods. So the next best option is cylinder. So most of the reactors in the world are cylindrical shape, so that our surface area to volume ratio will be minimum. These are the design objectives. So with this, we make this multiplication factor, that is one generation to next generation, how the neutrons are getting multiplied. I don't want 2, 3, 4 and all, because then the exponential growth will be there. We cannot control the reactor. We need exactly 1. Exactly 1. So in a side aspect, I will tell you, if you design a reactor and if you use all the cross-section library data, everything, you will not get this k equal to 1 with sufficient accuracy with the current computational tools. So if there are computer experts, there are so many challenges in this also. Suppose if instead of k, you have 1% error in estimating k with your most sophisticated computer tool, then it will become 1.01, right? I calculated my k for the reactor and it is 1.01, and I say my error is only 1%, but that reactor will be uncontrolled chain reaction, The accuracy required, and for the calculation, all the cross sections will go 1500 isotopes, measured nuclear cross sections for fission, absorption, everything. Challenge involved, I'm just giving a indication of, even though it is just a chain reaction, it is not easy to do mathematically. Now this process, how to achieve, there are many designs. Okay, what are the most common designs to make this K effective equal to 1? The most simplest one is a boiling water reactor. A reactor purpose is like any other thermal power plant, like coal or oil. We have to boil water, because this water steam will go to turbine and rotate it, and electricity will be produced. So the first option is we just fill a vessel with water and insert this fuel rods into the core, and you make the K effective equal to 1. Then there will be a sustained chain reaction, and fissions will be happening in every second, and that energy will be released to the fuel rods, and that energy will boil the water. And this steam will go to the turbine and make electricity. But here there is a problem. This is the initial designs. India also had 2 such reactors. Now they are not working. The problem is the water which have hydrogen that will absorb neutron and become deuterium, and it can even become tritium. And that tritium is radioactive, and this radioactive material will go to the turbine building. And with the current safety standards, radioactivity is not allowed in the turbine. Second thing is, since we are using light water here, you have to enrich the fuel. Okay, so that technology also you need. So the next option is to avoid this contamination in the turbine building. We have added one more loop here, this loop. So we separated the reactor core from the turbine using an intermediate loop. Okay. So here we don't allow the boiling of water in the core. We pressurize using a pressurizer, so that we keep the water at a very high pressure, like our pressure cooker, so that the water will not boil out. Boiling temperature will be very high. Then that pressurized water will be supplied to a heat exchanger or steam generator here. So this light water which is coming from the turbine, this will get boiled here and the steam will go to the turbine. Then you have to cool this steam here. That is where you see the big cooling tower. In nuclear reactor picture, you will see some big towers. The steam from the SO steam from the turbine will be cooled using cooling towers or seawater or something. Then it will come back here. Then it will collect heat from the primary loop and it will boil. And this is pressurized water reactor. This also use light water. Light water means H2O. But the problem, when you use light water, you have to enrich the fuel. The Kudamkulam 2 reactors we have, which is brought from Russia, both of them are this type. Okay, fuel also coming from Russia. Now most of the US reactors, these submarines, these nuclear powered warships, all of these systems are using this kind of pressurized water reactors. The challenge is to pressurize water and keeping high temperature. This vessel manufacturing is a big problem. Okay, very thick vessels have to be manufactured, and you need such kind of industrial support to make such forging technologies. So if you don't have pressure vessel, if you don't have enrichment technology, we have another option, and that is pressure tube design. So instead of pressure vessel, we make this pressure tubes. This is a horizontal reactor. In pressure tubes, we fill this fuel. Inside the tube, there is pressurized water. And around these tubes, we fill with moderator. This is the Calandria vessel is filled with moderator. And we can use natural uranium straight away if I use heavy water as a moderator. This is called pressurized heavy water reactor, or PHWR. This is the one India is opted for. Okay, India and Canada is running PHWRs, pressurized heavy water reactor. For this, we have to make heavy water. So India became an expert in making heavy water a long time back. We have plenty of heavy water plants are available. So we make heavy water. Instead of enriching uranium, we enrich water with deuterium. So we can sustain the chain reaction. So now these kind of reactors are run by Nuclear Power Corporation of India. Initially we started with 220 megawatt, then 500 megawatt. Now current reactors are made with 740 megawatt. Okay, 700 megawatt. So here also there is a steam generator. The heavy water coming from this will go to the steam generator, and light water will be boiled there, go to the turbine and do this. But in all these thermal reactors, all these reactors have moderator. With this thermal reactor, the problem is eta is always less than 2. The number of neutrons produced per neutron absorption. That number is 1.33 if you use natural uranium. It can be 1.35 if you use uranium-235. Now, if I want breeding, I need at least 2 neutrons. 1 neutron for sustaining chain reaction, 1 neutron for converting fertile to fissile, right? So I should produce by minimum 2 neutrons in every fission event so that I can convert this thorium and uranium to fissile materials. For that, we have to use fast neutrons. So fast fission in a plutonium-fueled reactor can produce more number of neutrons, more number of fuel than it consumes. So the third design is, okay, this actually PHWR, one picture is there. This pressure tubes I told you, this pressure tubes, view from this side view is given here. So these are the pressure tubes. You see the size of the reactor, the huge reactor, okay? Now this is only 220. If you go 700, it will be much bigger. And these are the fuel bundles. These fuel bundles will be pushed through one side. Okay, this kind of 12 bundles, 12 such bundles will be loaded through this hole. And these pipes are called pressure tubes, through which we supply the coolant. Coolant will be passed through these pipes. So this side, these pipes will be connected to this. Now this is pressure tube design. Okay. Now this is the Indian design. Next reactor is fast reactor. Fast reactor means we don't have to moderate the neutron energy. We can straight away use the fast neutrons, and we can use plutonium. Since I am not moderating the neutron energy, the fission probability is less. Okay. To compensate that, we enrich plutonium. Enriching uranium is difficult because uranium 235 and uranium 238 are chemically identical. Whenever I say uranium, they are chemically identical. The valence electrons are same. So 235 and 238 is different only in the neutron number. So whatever chemical separation methods we use, we cannot enrich uranium 235. So, but in terms of plutonium, if I have plutonium, I can separate plutonium and uranium very easily by using chemistry because they are different elements. So I can enrich with plutonium if I have plutonium. So fast reactor which use plutonium as a fuel, then I can get a eta higher than 2, and one neutron I can use for sustaining chain reaction, other neutron I can use for making more fissile material from the fertile material. So such reactors are called fast breeder reactors. So fast breeder reactors have potential to produce more fuel than it consumes. Now here the problem is I cannot use water because water is a moderator. I need fast neutrons. So instead of water, this coolant will fill this sodium. Sodium you cannot even assume as a liquid. The sodium is a metal, shiny metal, that we will boil. Okay, we will melt it and we keep the temperature 400 degrees Celsius throughout the life of the reactor. 60 years if I want to operate, this tank will be kept at 400 degrees Celsius throughout. If the temperature go below 200 something, then it will freeze. Okay, so that is the coolant we are using, and the sodium 23 have absorption cross section for neutron, then it can become sodium 24, which is radioactive. So again here like PWR, we have to give an intermediate loop here. So sodium will be passed through the coolant core, it will come here, then there is a heat exchanger here. With heat exchanger, the heat will be transferred to the secondary coolant, that is also sodium. Then it will give this heat to the steam generator where steam is produced, and the steam will go to the turbine. This is a very complex system. For example, if you look from the vessel, you cannot see what is inside. It's not water. You will see only the surface. Even maintenance, and you have to maintain at very high temperature. Even you cannot put sensor inside because at 400 degrees Celsius sodium, you cannot put even a neutron detector. Okay? So the challenges involved in this is very difficult, and Indira Gandhi Center for Atomic Research is designated for designing and constructing this kind of fast breeder reactors. Okay. Now, with this, I show you some. All this technology was known at the time we have started our nuclear reactor program in 1950s. So Homi Bhabha, who knows this thorium reserve of the country and the scarcity of other energy sources like oil and uranium, he made a roadmap how to use this thorium. He gave a roadmap, and that is called India's 3-stage nuclear program. In this first stage, we use the pressurized heavy water reactors, which is a tube-type reactor. We use natural uranium as the fuel, which have uranium 238 99%, 0.7% uranium 235, and this uranium will produce electricity, and this uranium 238 will become plutonium 239. Okay, because it will absorb neutron and become plutonium 239. Then we take that discharge fuel, we separate that plutonium 239. Okay, then this plutonium 239 we give as fuel to this fast reactor. This fast reactor have potential to make more fuel than it consumes. It's a fast breeder reactor. It have eta more than 2. Now here, this either I can load thorium or uranium-238 in the blanket so that that will be converted to fissile material. Okay. Now we will have enough plutonium or enough uranium-233 as discharge from the fast reactor. The next cycle, we use thorium-based reactors, advanced heavy water reactors, or molten salt reactors, in which this uranium-233, which is coming from the fast reactor, will be used as fuel, and thorium-232 we will load as blanket, and this thorium-232 will be converted to uranium-233. So finally, we want to convert thorium to uranium, right? That is our objective. That will be happening in only in the third stage of the nuclear program. Now, I will show it as a flow diagram. So the first reactor is PHWR, where natural uranium is the fuel, and the discharge is uranium-238. 235 will be consumed, 238 will be available, and also plutonium-239, which is converted from uranium-238. Now you use a fast reactor where I load this 239, plutonium-239 as fuel, and in the blanket I can load again 238 coming from this reactor. Then I will produce 239, and this loop will be keep on going. 239 will go back as fuel. Blanket, it will get blanket means around the core I will put some 238 fertile material. Whatever neutron leaking from the core will be absorbed in this blanket region. Blanket is this blanketing the core. So that will, in the blanket region, I will produce more fissile material. So that I will separate in the reprocessing phase. Then I will put it in the core. So that loop is this green one. We put it back in the core. Then again, after some time, we can add this thorium into the blanket. Once I add thorium, it will produce uranium-233. And this uranium-233 I can load into thorium-based reactors. Then I have to just supply thorium. Next phase is I have to just supply thorium to this reactor. It will produce uranium-233 in the blanket, and that will go into the core. So this vast reserve of thorium can be used in these reactors. So where we stand now is, before that, how we do this. Compared to other countries, you told at the beginning we told the problem of nuclear waste, right? What do we do with all the waste? So usually in America or France, all these reactors, what they do is they mine this uranium and plutonium. No, uranium, natural uranium, they enrich it, make the fuel, put it in a PWR. Whatever discharge comes, whatever plutonium it produces, they consider it as waste. They put it in the repository. Plutonium they won't use. Okay, most of the countries. India is opted like this, so we will not put it in the waste bin. We recycle it. We separate that plutonium and uranium. For that, we need reprocessing plants. Then we put this back to the fuel fabrication facility and we put it back to the fast reactor. Now, what happens is all the plutonium produced, all the uranium produced will go back to the fuel fabrication. Only the fission products will go to us waste. Now, fission products have one advantage. Fission products are radioactive, but they are of very short half-life. In 100 or 200 years, its activity level comes to the background level. All the higher actinides is having this million year half-lives. So handling such elements is difficult in a long time. They are radiation hazard. So India chosen a closed fuel cycle so that we can maximize the utilization of the resources available in the country. Now one more option is tried. That is, instead of going to the recycling plant, whether we can use, we make the fuel, this is advanced reactor, molten salt breeder reactor. So instead of coolant, we use the fuel itself as a molten liquid. We make uranium fluoride or plutonium, bismuth, iodide, and such salts we make, and we melt it. And instead of coolant, we circulate the fuel itself. And in the circulation loop, we add a chemical reprocessing plant. So we won't allow the fission products to decay. We don't allow the higher actinides to decay. We separate it in the beginning itself. Okay, and this kind of loop is necessary for thorium-based reactor because this isotope promethium-233, if it stay in the reactor, it is a very big radiation hazard. because it will absorb neutron and it will do an end-to-end reaction which will produce uranium-232, which have very high gamma emitting fission products and all. So to remove this promethium, we need to have this kind of reactor. Okay. Again, challenge for you. This reactor is not there in our country. Okay. So we have to make this reactor so that we can use our thorium reserve very, very efficiently. Now, if you see, this is here on the x-axis and the y-axis is the installed capacity. If I use only PHWRs, which use natural uranium with an open-ended fuel cycle, that means we are not reprocessing. Water waste coming from the reactor, we put it in the waste bin. Suppose if I do that, this is the capacity maximum I can achieve. This natural uranium will get depleted as I operate the reactors. But if I reprocess it and put it back into the first reactor, and if you use the thorium to produce uranium-233, and if you make use of thorium, we can have even 10 times or 20 times higher potential for energy production. Actually, these numbers are huge. 150 gigawatt electric is numbers are huge numbers. So accelerated energy production is possible. So these all are the science behind that. Okay, I thought I have told you the problems associated. Thorium recycling is a major challenge. Now we have perfected pressurized heavy water reactors which use natural uranium. We have 25 such reactors, large scale commercial reactors which is producing electricity. Fast reactor, we are operating last 40 years, one test reactor, fast breeder test reactor at our Kalpakam site. And new reactor is being constructed, and recently this year, it will be going critical, 2026. That is prototype fast breeder reactor. Now the history, if you see, 1946 we started before independence, TFR, and 54 we separated BARC, and we made this Atomic Energy Commission. And 56 itself we had our first reactor called Apsara, the imported reactor. Then 60 the Cirrus reactor came, as experimental reactor. Then came Dhruva and Purnima. This Dhruva and Purnima, the major contributions are from our Dr. P.K. Iyengar. And this Purnima is the one which provide data for the plutonium-based fission chain reactions. And the same data is used for our first weapon that is also plutonium-based. Then in Dhruva and Cirrus give important inputs for making PHWRs. In this slide, I have not given all the commercial reactors. We have made from 1960s, 70s to 2026. We have made so many thermal reactors. Only research reactors are given here. In 85, we started the second stage of our program, fast breeder reactor. Okay? And in 2026, this is a commercial reactor. It's the first prototype reactor, 1200 megawatt thermal, 500 megawatt electric, sodium cooled, plutonium fueled fast breeder reactor. Fuel loading started by our Honorable Prime Minister last year. Now, fuel loading is reached half the way. So in 2 or 3 months, you will read in newspaper, you just remember, we succeeded in the second stage program, okay? When you read the news. Third stage only I want your help. Now if you see 25 reactors are already operating, all are PHWRs and 2 are PWRs in Kudangulam. And you see all of these are aligned to the western side of the country because this is the region where we produce coal. So coal, the problem is shipping coal to a coal-powered plant is very difficult. You have to run so many trains. So this region we don't have coal. So all the nuclear reactors are aligned to the western side of the country because Chhattisgarh, Orissa, and Jharkhand are coal-producing states. Now, this is the very recent development. Last maybe 5 years. That is called small modular reactors. Now, for a long time, because of availability of oil and all, people were not much interested in making nuclear reactors. But now AI has come. AI needs huge amount of power to run the data surveys, and the problem with carbon emission has come. So countries are interested in nuclear, and they want factory-based reactors. That means you make a reactor in a factory, ship it through a truck, put it in your plant. Suppose Tata have a steel plant and need uninterrupted power supply. They want a reactor near to their steel plant. such a way that 20 years nobody has to look at that. No refueling, nothing. So just run in the background and produce the energy. Uninterrupted power supply for decades. So such reactors are called small modular reactors. Maximum power rating will be 300 megawatt electric, and that should be ultimately safe. It should work on fundamental principles like natural circulation, gravity. Such physics phenomena only should depend for safety, not active devices. Power failure happens, it should be safe. Human make mistakes, it should be safe. Such a reactor is called inherently safe reactor. So around 20,000 crore money is allotted for this project, and I told you the coal plants are being shutting down. So what we do with that? There are so many industry depending on that coal-fired plant. We have the cooling tower, we have the turbine, we have the grid connectivity. So whether we can replace the coal plant with this small modular reactor. So this is a requirement from NTPC. So we are designing such reactors. So not only us, Google, Meta, Amazon, Microsoft, everybody investing billions of dollars to this project of making modular reactors. They want a reactor in the background of their company so that they have to produce carbon-free energy. Suppose if you want to export steel from India, the first question the Europeans will ask whether the steel have any carbon footprint. If it is produced by burning coal, they will not buy your steel. So if your IT companies are using electricity which is consuming coal-powered plants, then the foreign countries will not accept it because they are shutting down their system, spending more money for energy, and they cannot buy this cheap. So all the industry people want this kind of reactors. So SMR is one solution. So this is the current status. With this, I think I will close. Those two pictures I will show. This is our first reactor, Apsara. Okay, this is a swimming pool type of reactor filled with water. And this is our that time Prime Minister. He only named it Apsara. And this is the Serenkov radiation, the famous Serenkov radiation, blue light coming from the reactor core. And recently, in the recent past, we have decommissioned this Apsara reactor, and we made another reactor in the same location called Apsara U. And this is the picture when the second stage, 1985, our FBTR got critical. And the person who is sitting here is Raja Ramanna, and this is M.R. Srinivasan, and this is our Dr. P.K. Iyengar, who was also significantly contributed to the program for plutonium-based reactors. This is the news came in the Nature magazine that time. Now I will give one quotation from our Iyengar sir from his book, Briefings on Nuclear Technology in India. It is only through science that you can develop technology for human welfare, and it is only through that we can sustain the present rate of growth and needs of the human civilization. There is always a danger of complete annihilation by a hydrogen bomb, but that of course depends upon the wisdom of the people. It is therefore necessary that people in general are exposed to the scientific curiosity and a process of decision making which should be based on rational thinking and scientific way. Decision making on scientific thinking and rational thinking. This is, in Nehru's terms, it is called the scientific temper of our country. And that is most important thing. When you go out of the college, the first asset you should have is rational thinking and scientific temper. Why it is important? I will show one more slide. This is the last slide, sorry. This is an SNR 300 fast reactor which is made in Germany. And after completion of the construction, they had the fuel ready to load. But there was huge public opposition. No nuclear, no nuclear. Then what happened? They shut it down. The core never loaded. And it is one of the most expensive human waste ever created. Around in the globe, the most expensive waste produced is this thing. And they sold it as like scrap. Some amusement park people purchased it. Right now it is a amusement park. So rational thinking is important. You want energy sustainability or amusement park is our choice. Thank you.
Thank you, sir, for that insightful and thought-provoking lecture. We will now have a short interaction and Q&A session. The floor is now open for the questions. May I request participants to keep their questions concise. Students, if you have any question, make use this opportunity.
Okay, I will ask one question. Oh, you ask. Please.
Sir, what would be the courses or programs that we can pursue to know more about this after the degree?
To that?
After our degree, what would be the courses or internships or programs that we can pursue
Yes,
to
yes.
know more about this?
No, in our actually nuclear energy only, I think IIT Delhi had a program for MTech, like regular academic program. Most of the programs are like PhD and above only. Then there is a postgraduate diploma that is also awarded to the people who are joining the department. So recently, I think Kerala, some universities thought of starting this. Calicut University has some nuclear in the syllabus only, but per se, this is not in the course of most of the universities. Manipal University have some courses in MTech and MSc, I guess. But actually, for joining the department, you don't have to know the in and outs of the nuclear technology and all. You have an MSc or a BTech, you are always welcome to join our department. Actually, this is a public outreach also. So you please join. You have to write some exam called OCES, Orientation Course for Engineers and Scientists. And otherwise, you can attend the GATE. With the GATE score, you can attend the interview. Then you have to undergo a 1 year BABA BRC training school at Mumbai. Then after completion of 1 year, you can join as a scientific officer C in the department. So, yes, of course, career will be very simple. And at many occasions, for example, recently when I was working for 16 years now, when the first time we have the neutron count detector responding in our prototype fast breeder reactor, after loading the 25 assemblies, we got the readings. That kind of moments you can cherish throughout your life. So there is nobody in that room, only we few will be there, and there is no glamour, but still, but for your own, that will be like a great satisfying thing to see, and you know that this is going to contribute to the growth of our country. So, yes, you write the exam, OCES. Okay, you visit the website for OCES. And other than this, IGCA directly recruit a scientific assistants and technicians, and at different levels are their vacancies. And one more thing, even though you are if you join as scientific assistant or officer, you can still do PhD, you can do postdoc, you can go foreign country and do postdoc. So such options are still there because we have our own university called Homi Bhabha National Institute, where you can register for PhD. If you are working in any of the DAE's constituent plant, you can still have a PhD with our university.
Yes, sir. Thank you, sir. And it's very rare that we get to meet a nuclear scientist. So, we have all heard about Iyengar, sir. About him, we did hear. I think students would like to know about you because I understand you studied in Kerala. What are you basically? How did you get in there? I think it would be nice to hear from you.
If you ask me personally, if this lecture is happening here, I will be somewhere there talking only. So, so don't worry that if you are sitting in the back bench or if you are not even in the auditorium, don't worry. You can still become a nuclear scientist. It's not such a big deal. I was studied in a government school in Chadayamangalam, Mahatma Gandhi Government Higher Secondary School. Then later I BSc pre-degree and BSc I did in St. John's College, Anchal. MSc was from Kochi University. After MSc I joined BRC training school. Then it was through OCS exam only. So So if some of you think that becoming a nuclear scientist is not achievable, don't think like that. Okay, everybody can be, but it's a government job, so an exponential growth in salary, career, and such high-fi dreams if you have, it will be limited.
Thank you, sir. Thank you, sir, for the very informative talk. I have a couple of questions. First one is, so in your talk you mentioned about India using plutonium as the fuel, and other countries they are reluctant to use plutonium. I would like to know why. And second question is like, so we talk about the EV. So we are in the EV era, right? So I was just thinking like, do we have research going on where we can see a future vehicles running on nuclear fuels in the form of a battery or in a compact form? Thank you.
So, first question is why plutonium is not being used, because they have other sources of energy. That is a major reason. Cost effectiveness. You know, in Western countries, these plants are run by private companies. And the sodium cooled fast reactor is a very sophisticated technology, and the money investment required is high. And since you have plenty of uranium, America have large deposit of uranium, and they have large availability of oil. So they consider plutonium as a proliferation risk. So they don't as a contamination risk, and they keep it safely in the background. Now countries like Russia and India, they have fast reactor. Russians have fast reactor. Uh, France tried. They made a 1,000 megawatt super phoenix, a very big reactor, but due to sodium technology, sodium cooling is very difficult. So they had some leak events and all. Japan tried. Many countries failed also. So India is also attempting. One reactor we run for 40 years without any sodium leak and all. So now commercial scale reactor first time this year only it is coming online. So let us see whether how we progress. Now using a nuclear material, whether we can hand over nuclear material to individuals. That is a problem, because you may not be knowing that there is not only nuclear bomb, there are called dirty bombs. I think Vishwarupam, some movie it is there, that Kamal Hassan in the Dows, they will keep the nuclear material. In beds, he is trying to spread the nuclear material through beds and all. So if you give nuclear material to public, that is not possible, I guess. But still, there is a large amount of research going on in our center too to produce hydrogen. So nuclear have very high temperatures, like 400 to 650 degree. That heat can be used to split water, and by that we make this hydrogen batteries. And that hydrogen we will give to vehicles or any home supply and all. So hydrogen battery production is one of the targets. Instead of giving directly the nuclear fuel, we give like hydrogen. FBTR currently have a hydrogen plant.
Good afternoon, sir. First of all, thank you for your wonderful presentation. And my doubt is, or my question is, why is thorium considered as the most important nuclear fuel for India? Thorium.
Thorium. Thorium because of its availability. For example, uranium is available like 20 to 30,000 ton in the globe. But we have thorium like lakhs of ton. And thorium have high neutron absorption cross section for converting to uranium-233. We can easily convert to uranium-233. The challenge is separating that uranium-233. Whenever we separate uranium-232 also comes with that. And that problem we have to solve. And chemistry-wise, there is a challenge that thorium oxide is highly stable compound. So whatever process we are using, like mixing with nitric acid, concentrated nitric acid, that is not working in thorium. So we have to find out alternate ways to reprocess the whatever output coming from the thorium. So thorium is because we have thorium. So if India is blessed with anything, that is thorium. So we know the Padmanabha Swami temple treasure, the actual treasure is in this sand. Okay, so actually China has advanced pretty much in this thorium based system, and we too hope near future. We have already a reactor running in uranium-233, that too at Kalpakkam. That is called Kalpakkam mini reactor, Kamini reactor. So thorium we have loaded in FBTR. We produced the uranium-233, and we reprocessed it. We used it as fuel. So thorium-based reactor is already running, but not in the commercial scale.
So I have a doubt regarding the nuclear waste management. In our country, we you recycle most of the nuclear waste. What about the control rods? Do we also recycle them?
Control roads activity wise is very less because it's more on its half life is very small. Okay, I will put the perspective. You can sit the perspective like this. Suppose all the nuclear waste humans have ever produced, if you just distribute across the globe, it will not affect even the background. Okay, if you spread all the nuclear waste in ocean and air and then on the land, the change in background radiation will not be measurable. That is the but we cannot do that, of course, because if it concentrates somewhere, it can cause the radiation damage. But the thing is, there are other technologies like accelerator-driven systems. These are like we use an accelerator to accelerate protons. Then using that protons, we produce neutrons, and these neutrons will kill this radioactive waste. So this research is also going on in India also. I have a plasma research laboratory and all. So we whatever stockpile we have in the backyard of our nuclear reactors, that can be incinerated. So fast reactors do a very good job in incinerating this waste, and such reactors are called washing machines, nuclear washing machines. So the waste you can be loaded as fuel, and then the output will be less of waste. But still, that fission products, whatever form, like cesium, iodine, and all, that will be there. That will be separated and stored in canisters. So after 100 or 200 years, that will not be having any radioactivity. It will be in the background level. Ask. ചോദിച്ചോ എല്ലാരും ഒരുപാട് ചോദ്യം ചോദിക്കുക എന്നൊക്കെ പേടിച്ചാണ് ഞാൻ വന്നത്.
Good afternoon, sir.
Yes.
So you were talking about nuclear fission, right? So can you tell me the chemical and radiological hazards associated with nuclear fission?
Yes, hazard is only because of the radioactivity of that fission products. So that fission products is radioactive, and that radioactive is one way good also. You know, whatever we are running X-ray machines, MRI scan was actually NMR, nuclear magnetic resonance. Since people are afraid of nuclear, we changed the name to magnetic resonance imaging, right? And for cancer treatment, everything we are producing these radioactive isotopes. So whatever useful isotopes we are using in the industry, whatever not useful, that we have to dispose. So of course, it is a challenge, but it doesn't mean that that challenge cannot be solved. We have already solutions, and the stockpile of our radiation that is very limited only, because E equal to mc square. The amount of fuel we are using in nuclear reactor is much small. Okay, the fast reactor core diameter is 2 meters, maybe this much length, and height is 1 meter. This is the core of a reactor which produces 500 megawatt of electricity, and 1/3 of that fuel will be replaced after 6 months. So you can bring the total fuel in a truck for many years actually. That much only the quantity wise, if you say by kilogram wise. So managing that waste is not that difficult.
Hello, sir. My question is regarding e-waste management. We use thorium as a main source of fuel, and one of the crises that we face right now is waste management, especially e-waste or electronic waste management. How about we use recycled e-waste? It's hard to dispose e-waste and recycle it. However, we find new methods to recycle e-waste and use it as another source of fuel for the nuclear power plants.
You are saying e-waste, no?
Yeah, electronic waste.
Electronic.
Yeah.
Okay. That I'm not an expert actually. E-waste recycling, sorry, like, a reactor cannot do help there actually.
Thank you all for the engaging discussion. May I may I now may I now invite May I now invite our esteemed dignitaries of the dais to join Dr. Anuraj VL on the stage.
Hello. Hello. Hello.
As a token of appreciation, we now invite Dr. Arunan C., Senior Principal Scientist, KSCST, to present a memento to Dr. Anuraj VL. Thank you. To formally conclude the proceedings, I invite Dr. Jaya Jacob, Junior Scientist, to deliver the vote of thanks.
It was indeed a very engaging day. Because we could hear a lot about the future technology, and we have the future of the country sitting in front. And it's my duty to formally propose a vote of thanks. Moving on to my duty, at the outset, I thank our speaker for Raj VL, Scientific Officer G, Iyengar, for his very insightful lecture and for having graciously consented to be our speaker for the day. Thank you so much, sir. It was a very engaging session because a lot of things, from the simple things to the very complicated uh, chemistry part, was discussed in detail, to the understanding of even a biology person like me. So thank you, sir. And we look forward to a lot of advancements in the field from your organization, and I hope the country will advance in this technology with an effective leadership from the organization. Thank you, sir. Moving on, I thank Dr. Arunan C., Senior Principal Scientist, KCST, for having grace the occasion. He's also the joint convener for the Kerala Science Congress. So, to the participants, the Kerala Science Congress is scheduled from the 30th of this month to the 2nd of February. So, I hope that you have registered for the event and looking forward to your participation in the event. Thank you, sir, for the welcome address. Now, moving on to the associate partner for this event, Fatima Mada National College. Special thanks to the president of the function, Dr. Cynthia Catherine Michael, for the presidential address, and also to the management staff, faculty members of this institution for the wholehearted support in the successful implementation of this program. Thank you. Thank you. Special thanks to Dr. Sharon BM, scientist KCST, for introducing Dr. PK Iyengar to the audience, and also to Dr. Shaiju PN, Assistant Professor of Botany of this college. Thank you, sir, for introducing the speaker and for the overall coordination for this program. We could see him coordinating each and everything from the time it was planned. Thank you, sir. Thanks to Dr. Arjun from KCST for coordinating the program from KCST side. A special thanks to the media team and for all the faculty members of this institution, and to the participants for your patient hearing. Thank you all. Have a great day.
Thank you, ma'am. Before we disperse, a few important announcements. E-certificates will be sent to your registered email IDs. For updates on the 38th Kerala Science Congress, please follow our official social media handles and visit the KSC website. Thank you all once again for your presence and active participation. Wishing you a pleasant day ahead. Thank you.